Video, we're going to go over magnetism and magnets. We're going to start off by going over some definitions and some rules on how to draw magnetic fields. All right, let's start off with the definition of a magnetic field. So we discussed fields before in physics. It's come up with gravitational field, which affects mass, electric fields, which affects charge, and of course now we have magnetic fields. So the idea of a magnetic field, by the way, the variable for magnetic field is the capital letter B. I'm not quite sure why we choose the letter B, but that's what we use. Is a field that describes the magnetic force on three things. Now, these three things are unique because before, in all the previous fields that we just discussed, whereas gravitational field, it just affects objects. Electric fields affect just charge, right? So there's a one-to-one correlation. Magnetic fields actually affect a vast array of things. And the three things are moving charge, current in a wire, which is essentially a moving charge, and other magnetic material. Now, the last one makes sense, right? If you have two magnets and they can interact with each other. But the moving charge and current in a wire, that should be new information, and that's what this unit is all about. We're going to dive into why that's the case. Okay. All right. So if a magnetic field exists, that means that magnetic force will be exerted on either one of those three things, or maybe all of them. All right, so here are the rules. The rules for drawing magnetic fields. So as I'm describing the rules, I'm just going to start off by showing you a bar magnet here. So here we have a bar magnet. We have a north side and a south side. So rule one, the if we have a north side and a south side, that's actually rule one. Uh, Magnets or magnetic fields, okay, must be a dipole. And there is actually a physics formula behind this. But when I say it must be a dipole, if we were to break this word down, di means two and pole is just pole, right? North, south. And this is different from electric fields, or when we draw electric field lines, because with electric field lines, we can either have just a positive charge or just a negative charge, and that'll be fine. But for magnetic stuff, it must be both north and south. Okay? All right. So when we're drawing field lines, the vector must come out of the north and the vectors must go into the south. And because we have this idea of a dipole, whenever you're drawing a field, what you're looking for are these closed loops. Okay, so this is rule one, must be a dipole, and you're looking for closed loops. And the idea of the closed loop is if a field is coming out of the north, okay, all along the field, we have all these field lines and eventually loop back into the south. Now, inside the magnet, the rules still apply. So a lot of people think the magnetic field exists only outside of the object, but what we have discovered is that the magnetic fields are actually inside the object as well. And so here, if this is the south side, we can just keep on drawing these field lines, okay? So I'm just drawing each individual field line, right? You could just draw it as one long field line, okay? But essentially, you just get a lot of different vectors all along. Now, it's important to note here, I drew one giant loop, but if we were to be technically correct, okay, these are the field lines at that point. So for example, at this point right here, we have a field line going out this way. And the way we know the direction of the field line is by using a compass. Okay, so the tool that we use to say, hey, which direction is north or which direction is the south is if we use a compass. So the magnetic field and the compass, right? So the magnetic field aligns the compass along the direction of the field lines. So if we were to put a compass right there, okay, we would see that the compass arrow points in this direction. And if we were to put a compass, let's say right here, we would see that it points in this direction. If we put a compass right here, we would see that it points in this direction. And we can keep on doing this so that we just get continual field lines. And in fact, in our lab, this is what you're going to be doing. You're going to be putting the compass all along different parts of the magnetic field to see the direction of the field at that point. So if we have all of these vectors, and if you're to line up the vectors tip to tail, what you end up with is this loop that we drew before. But technically, there's all of these field lines all along here. Okay, and the field lines show if we were to put a magnetic material at that point, okay, what direction is the field that the object is experiencing. All right, so those are the rules. The vectors must come out of the north. It has to go into the south. And here's a very important rule. This is a ginormous physics rule. In fact, if you break this rule, you might be on the verge of a ginormous breakthrough. The idea is the monopole can never exist. Okay, so mono just means one, which means that you can never have just a north side. You can just never have a south side. A north and a south must exist. So let's go over into this idea of why that's the case, right? So if I were to go back to my drawing here, I had a magnet. Where's my magnet? I'll be right back. All right. So if I have a magnet here, right? If I were to break this magnet in half, essentially what I have is two magnets. Okay, and both of these magnets can be described as a north and a south. Right, both have a north and a south. And if I do that again, I now have two more magnets. Right, and I can continue doing this for a very, very long time. If I do that, what I end up with is I get to a smaller magnet, a smaller magnet, and a smaller magnet. Now, this was like the foundation of physics way back with the ancient Greeks. They thought, if I keep on chopping an object in half, there's going to be a point where I'm going to get down to the base material of the object. And that is where the word atom comes from. Okay. Now we've learned a lot since then, and we learned that it's not like a cue ball that the Greeks thought it was, but it's actually built up of protons, of neutrons, and of course electrons. And the idea that a monopole cannot exist actually comes from that electron. Okay. So if I were to go back to this drawing here, just to show you this chopping in half motion, if I were to chop this magnet in half right there, we can see at this point, right, this is the butt end of the arrow, so this is the south, okay, and this has always been the north, right? But if I were to chop this magnet again right here, okay, uh, at this point, this is now my north side, and this right here becomes my south side, and this is still my north, right? So every time you chop a magnet, you just get another smaller magnet. All right, so let's go down to like if you keep on chopping it down, what do you end up with? You get an atom. So where is the magnet in the atom? Well, that actually comes from this idea right here, and we'll go into more detail later. But the idea of a moving charge. So if we were to look at a very basic elementary sketch of an atom, right? We have the nucleus and we have electrons that are spinning around. So it's actually the electron that's spinning around that's creating what we call a magnetic dipole moment. I'm going to type this out. Magnetic dipole moment. Okay, and so this magnetic dipole moment comes from a spinning electron. Let's see. Uh, Comes from spinning electrons. All right, so I'm going to try to really sketch this out. But if we have a electron here, right, and this electron is spinning around like this in a loop, what you end up with is, if we were to visualize this in our human brain, you get a magnetic field. So the spinning electron creates a magnetic field, and that is really, really, really cool. It's one of the most craziest things that we can like talk about in physics. How a moving electron creates this thing called a magnetic field. All right, but the important thing is that this magnetic field that is created, okay, from the electron has a north side and it has a south side. So even if you keep on chopping this magnet up all the way down to the electron, even the electron itself will have a north side and a south side. All right. All right. So how can we describe this in terms of like a formula? So this actually goes back to way back in the beginning of the year when we're talking about flux. Okay. So if you remember, flux is taking a look at how much of something goes into and out of a area. And before, we were thinking about electric flux, right? So that's the symbol phi for flux, and we wrote phi e. Okay, and this looks at how much electric field can go into or out of a certain area. So, for example, if we had a rod and this rod is positively charged, right, and we were to take a look at that's like the E field, and we were to create like a window right here. So, according to this window, we have a E field definitely coming through the window. Okay, and that's only in one direction. But the idea of this closed loop, okay, for a magnetic flux, our magnetic flux must always be zero. And so this is the idea of a closed loop. So here in the electric field is only going in one direction. So it can never loop around and come back. But with a magnetic field, if I were to draw this magnet here, right? And if I were to draw let's draw a box. If I were to draw a box around, this is my Gaussian box. This is my Gaussian box around the magnetic field. Okay, there we go. I can see here the magnetic field comes out of the box. So this is flux out. But when this loops around, hey, that same field is going flux in. So with this flux out and this flux in, what we get is a net flux of zero, always, for a B field. And this is due to a closed loop, okay? And this is due to the dipole, right? Fundamental rule of magnetic fields. All right, so in class, what we're going to do is we are going to be working with magnets, and we're going to try to draw and sketch the magnetic field lines to the best of the abilities. But the important thing is that field lines always come out of the north into the south. What we're looking for are these closed loops, and the way that we know the direction of the field line is by using a compass. So the compass will tell us what direction it's pointing, which brings me to my final idea. Right? So let's go to the Earth. I'm going to draw a Earth there. So this is the north and this is the south of the Earth. The Earth has these are different land masses. This is my Earth. So if you ever use a compass to navigate your way around, the cool thing about the compass is that here this is what we call geographic north. Okay, but the compass that aligns to geographic north, a compass, the north side of the compass will point towards north. Okay, but it's important to know that the compass aligns itself to the magnetic field, and so this north side cannot be attracted to the north point of the magnetic field there, because much like the fundamental charges, okay, like charges repel, so like poles also repel. So for example, if you have a north side here and a north side here, this is a repel. But if you have a north side and a south side, these will attract. So if the compass is attracted to the North Pole, okay, that is actually a little skewed description of what's happening. The compass is attracted to the geographic North Pole, but the North Pole actually is so if we were to put a giant bar magnet in the middle of the Earth, the North Pole is actually a giant South Pole, and the South Pole is a giant North Pole. So the compass is attracted to the north, the South Pole, which is at the geographic north, right? Isn't that crazy? That's bizarre, right? And the reason is because the north side of the compass must attract to the south side of the magnet over there. All right. That's where I leave you off. In the next video, we're going to go into a little bit more of the electric dipole moment. But until then, I'll see you next time. Bye bye.